Okay, so welcome to the CEEE 2310 Digital Systems Exam Review for, I believe, the second exam. So I'm Megan, there's Varsha, and then Kawan. So the topics we're going to go over muxes, decoders, encoders, adders, subtractors, and comparators, flip-flop, timing diagrams, registers, memory, and then information as bits, floating point, fixed point, and binary arithmetic. So we start off with muxes, decoders, and encoders. I put them all on one slide here just so you can see the difference between them. So first, if we start off with a mux you can think of it as like a train track. Basically, we have four or multiple inputs, in this case 4, and we select only one of them to pass through. So like I can put certain select lines to say I want I1 to go through, the data in I1. Or let's say instead I want I3 to go through. But we can't have like multiple lines going through at once, only one. And we select those through the select lines. And I have the truth tables right here. But basically, let's say I wanted to have the data from I2 go through. So I want the output to be I2. I would put my select lines as the binary equivalent of that subscript, which is 2. So the equivalent of 2 in 2-bit binary is 1, 0. And so if I show here, so it would look like 1, 0. So then this line here would go through. So let's say instead that my input was 1, 1. Well, 1, 1 select. 1, 1 is equal to 3 in decimal. So that means I3 will be the one that passes through. And I3 will be the data that comes out. So that's for a mux. For an encoder, we have multiple inputs. So I forgot to write this for the mux, but I'm gonna say one output and multiple inputs. So if you ever have something that's multiple inputs, one output, it's most likely a mux. And then we have multiple inputs, but in this case, instead of one output, we have multiple outputs. It's just less outputs than inputs. And for this one, I really want you to look at the truth table, and you'll see that these inputs are all 1 hot, which means only one input is on at a time. With an encoder, you do not have more than one input on, so you cannot have D0, 1, and D3 as 1 and the others as 0. That's not how an encoder works. Basically, depending on which input is on, the output will be the binary representation of it. So I'll write that here. So let's do an example. For example, if we have, let's say, D2 is on and all the others are off because we're doing 1 hot encoding, then that means that the output should be the binary equivalent of this subscript. So that would be in 2-bit binary, that'd be 1, 0. Oh my god. Sorry, I'm not used to the double tap. It's throwing me off. Anyways.
Auto deselect, I can change that.
It's okay. Happens every time. Anyways, so we can look at this truth table and you'll see. So if we have D0 as on, the output is binary equivalent 0, 0. We have D1, binary equivalent 0, 1. We have a D2, binary equivalent 1, 0. And then D3, binary equivalent 1, 1. Next, we have the decoder. The decoder is essentially the opposite of an encoder. So you have less inputs than outputs. And in this case, if we look at the truth table, you'll see that the 1 hot encoding is actually in the outputs. And now the binary equivalent is the inputs. So if by looking at this truth table, we see if the binary inputs is 0, 0, then Q0 is going to turn on. And if instead we have binary equivalent 0, 1, then we have Q1 turns on, because that's the decimal. 1 0 turns into decimal number 2, so Q2 turns on. And 1 1 turns into decimal 3, so Q3 turns on. So you'll never have a case where multiple outputs are on, so this would be invalid in this situation. It's always one hot. And doing a small example using the actual gate itself, let's say we had input 1 0. 1 0 is 2 in decimal, so that means Q2 would turn on and all the rest are off. So it's good that you know the difference between all of these, and I like to think of it as just like MUX has one output, so it's like train track, you pick up a spot, or you pick one input to go all the way through. Encoder has multiple inputs and less outputs, and then decoder is the opposite with less inputs than outputs. So we have adder and subtractors. So in this case, this is for the add, so I'm saying to add 5 plus 2. A and B are our inputs, so in this case 5 will be A and B will be 2. So converting that to binary, 5 in 4-bit binary is 0, 1, 0, 1. So A3 refers to the leftmost bit, and A0 refers to the rightmost bit, the least significant, right? And then B, we have 2 in decimal, which is 0, 0, 1, 0 in binary. So now we have these gates here. These are XOR gates. And an easy way to remember what XOR gates do is if the inputs are different, then your output is a 1. So if I do a small little truth table real quick on that, that would mean that input 0, 0 was, they're not different, so that's 0. The middle two are different, and the last one is, they're the same value, so you get out a 0. So in this case, this XOR gate is connected to both this add subtract control line and our B inputs. So we have to figure out what this add subtract control line is. So with add subtract control lines, when you want to add, you make it a 0. And when you want to subtract, you make it a 1. And you'll see how that kind of works out with these gates in a bit whenever we walk through it. So in this case, since we want to add, we want our add subtract control line to be 0. So I'm going to go ahead and just write it above right here, just so it's easy to see what the inputs of the XOR gates are and we don't have to keep tracing back. So for this XOR gate, what comes out of it, in this case, we have, with an adder, we always want to start from right to left. And that's because whenever we, let's say like add binary, we always start with this, the least significant bit, and then we carry over like so. So in that similar case, we're going to do the same thing, but with the actual hardware itself. So we start with this right one here, and we say, okay, coming out of this XOR gate, we have 0, 0. They're the same bit, same value. They're both 0. So what comes out of the XOR gate is a 0. And then A0 just goes straight into this full adder. This carry in is connected to the add subtract control, which we set to 0 because we're adding. So now we have these 3 inputs into this adder, and we're just going to add them all up. So 1 plus 0 gives us just a 1. The answer will go down here, and we have carries. So in this case, we didn't have to carry because we didn't have a situation where we add a 1 and a 1. So we didn't have this carry up here. So whenever that happens, you just put a 0. Going to this next one, this XOR gate has a 0 and a 1. Those are different inputs. So what comes out of an XOR gate is a 1. And this A1 just goes down. Now we're adding a 0, a 1, and a 0. So once again, we have 1 coming out and no carry. A 0 as a carry. This XOR gate, we have 0 and 0 inputs. Oh, yeah, 0, 0 inputs. So in this case, they're the same. So what comes out is a 0. And then this A2 just comes down to here. So we're adding a 1, a 0, a 0. So what comes through is a 1, and then a 0 as a carry. And then lastly, this XOR gate is a 0, 0. They're the same. So we have an output of 0. This A3 comes down. We're adding a 0, 0, 0. What comes out is a 0. And once again, we have a 0 as a carry. So then just to check our work, whenever we do 5 plus 2, we should be getting 7. So the decimal equivalent of this binary number should be 7. So this answer was 1, 1, 1. And if you convert that to decimal, you should get 7. So that proves that we did this correctly. Let's move on to the subtractor version. So in this case, we're doing the same exact inputs, but now we're saying, okay, let's subtract them. 5 minus 2. So A is 5, B is 2. Once again, I'm going to put in my inputs. 5 as a 4-bit binary is 0, 1, 0, 1. And B as a 4-bit binary is 0, 0, 1, 0. Or I should say 2 as a 4-bit binary. So now since we're subtracting, we want to subtract, we're going to set this control to 1. And you'll see how this kind of changes this up. So now what's connected to this, all these XOR gates are a 1. So once again, starting on the right side, we have this XOR gate. We have a 1 and a 0. Those inputs are different. So what comes out of the XOR gate is a 1. This A0 value comes through. And this carry in is connected to this add subtract control, which we set to a 1 because we're subtracting. So now into this block, we have a 1, a 1, and a 1. So most of you are familiar with whenever you add 2 1s, you get a 0 coming out and a carry of 1. But some of you guys might not be too familiar on what if we're adding 3 1s. It kind of looks more tricky. But you can just think of it as, okay, 2 of these ones are going to turn into a carry, right? If we keep adding, let's say, let me erase that and do that better. If we keep adding, two of these are going to turn into a carry for the next line. And what remains is, and then what comes out is a 0. And what remains is a 1 plus a 0. So whenever you add 3 1s, you have 1 coming down, and then you have a carry of 1. So we're going to apply that here. So in this case, we have 3 1s added. So 2 of these are going to be made into a carry, and then 1 of them is just going to come down because it's added a 0. This next XOR gate, we have 1 and 1. Inputs are the same. So we have coming out of this XOR gate a 0. This A1 value comes through. Now we have a 0, and a 1 added together, which just gives us a 1 coming out and then a 0 carry. This XOR gate has a 1 and a 0. The inputs are different. So coming out of this XOR gate's a 1. We bring down the A2 value, and we get 1 plus 1 plus 0. So that gives us 0 coming out, 1 carry. And then this XOR gate, we have, once again, different values. So 1's coming out of the XOR gate, bring down the A3 value, and we get 1 plus 1 plus 0, which gives us 0 and a carry of 1. Remember, whenever we subtract, we always ignore the carry out bit, the very last carry out bit. So in this case, an answer of 10011 would actually be wrong. Okay, we ignore the carry out bit, so your answer is 0011 or just 11 for short. And we can check this too, because 5 minus 2 should be 3 if we're just working a regular decimal, and the decimal equivalent of 11 is 3, which proves that we did this correctly. Next, we're going to work with comparators. So the way comparators is slightly different than adder subtractor, in which adder subtractor we work from right to left, least significant to most significant. we're now going to work the opposite way. We're going to work from most significant to least significant. And I'll explain that in a bit. But basically, slightly different notation for those who aren't familiar with this. What it's basically saying is we have A3, A2, A1, A0. These are all like the placeholders. So we have a 4-bit. Basically, this notation is saying we have 4-bit. We're going from the 0 placeholder to the A3 placeholder. And so we want to represent 3 in 4-bit binary, essentially. So that would be 0, 0, 1, 1. And then the same thing for the B input. 4-bit binary of 6 in this case. So that would be wait, wrong one. Yeah, it would be that. Okay, so now we're plugging in our inputs. Over here 0, 0, 1, 1. And then over here the B 0, 0, 1, 0. So once again, I said we're going to start on the left side. Okay, so first we have to make assumptions here for us. It's connected to something else, but so we have to figure out what we want these greater than, less than, or equal to be. There is only one way to start these out unless you're told otherwise, and that would be for equals to be set as a 1. Now why? Because if I set, instead of this, if I set either greater than or less than as a 1 first, then it doesn't matter what my inputs are, that will carry through all the way. Because the moment you get a greater than, it's going to stay greater than all the way through. The moment you get a less than, it's going to stay that way all the way through. Now, that may be like, well, why is that? Why do we not care about the rest? Well, I'm going to do that with a short example. So, actually, let's say I had 8. So this is binary equivalent of 8. Okay? Now, I'm saying, okay, well, I'm comparing it to something else, right? Another number. Let's say I'm comparing it to a number that has all ones next. Because you might think, oh, all ones after, what if that changes it? And through this first bit, we find that the top number is greater than the bottom number. But what if all of this that comes after somehow makes it so the bottom number turns greater? The way that binary is written is that's impossible, because in this case, even if every single number after is a 1 compared to zeros on the top, this will just get you 7 in decimal. And that's true for any case. You can try it with any different one. So let's say we had like 4. Even if the number we're comparing it to next, all of the rest is ones, that's still 1 less, just because the way that binary is made. So that is why once you find out that first initial relationship of, oh my god, this is greater than or this is less than, that's going to be true no matter what comes after. So in order to make sure that we actually compare these two numbers, we have to set it so that we think that they're equal for now, until we actually start comparing them. So I'm going to move down. This is moving down all the inputs. This is A3 and B3. I'm going to write over here A2, B2, A1, B1, and A0 and B0. So starting at this digit 3 block, I'm going to compare 0 and 0, these two inputs, they're equal. So I'm going to say that the output of this is equal. Okay, and less than and greater than are 0. Next, comparing. Whenever you compare these, you want to compare A compared to B, so left to right. So A is less than B. 0 is less than 1. So now I finally have something other than equals. I finally have a relationship. So what comes out is that less than is a 1 and everything else is 0. And now we don't look at the rest. We just bring that all the way through. Because like I said, no matter what comes after, nothing can change that relationship just based off how binary is made. So even though right here, 1 and 1 are equal to each other, we do not say that this output here is equals. We don't even look at that. we just carry that relationship that we found here. This is where we finally did our last comparison, and we just carry it all the way through. And then that's how you do comparators.
Hello everyone, I'm Kawan and I'm going to be going over part 2, which is flip-flop timing diagrams, registers, and memory. So let's go to flip-flop. So flip-flop timing diagram. I just wanted to emphasize that for this class, we'll only be looking at the rising edges, which are these parts here. So every time you're looking at the clock, you're always going to look at these parts only. And this is the input, D is the input, and Q is the output. So let's practice. So when you start looking at a flip-flop timing diagram, I would recommend first looking at the reset button, because that's gonna be your priority. Because if reset is at 1, you know it'll be 0. Your output has to be 0. But first, let's look at the output, which is what we're gonna be working on. And for the first one, we know that it's unknown, so we'll put it at the middle between 0 and 1, because we can't tell what it is since we start on the falling edge. And so let's look at the clock now. So like I said before, we look at the rising edge. So let's look at the rising edge. Enable is 1, so we should be good. Input is at 0. So if the input is at 0 here, it means that our output has to be 0. So let's go 0 until the next rising edge. Once we get to the next rising edge, we're going to look at the input again, and we're also going to look at the enable just to make sure it's at 1. If enable is at 1, it means that you change accordingly to the input. But if the enable is at 0, you just keep whatever output you had before, and you don't look at the input. So let's look at the next rising edge. So the next rising edge, we have enable 1. It's still 1, and the output is at 0. So we're going to stay at 0, and we're going to go to the next rising edge. So next rising edge, now the input is 1, while the enable is also 1, which means that we're going to be at number 1. So our next output should follow all the way to the next rising edge as a 1. So let's look at the next clock. The input is also 1. The enable is at 0, so we would keep 1 anyway, but it's good to know that it's at 1, so we'll just stay as 1, as number 1. Now we look at the next rising edge, and we see that the input is at 0, but because my enable is at 0, we're just going to keep the same output, and we're going to move on to the next rising edge. So let's keep it as 1. And then now we're going to look at the next rising edge. The next rising edge is 1, and the enable is 0, so we have to keep it up as 1. And we move on to the next rising edge. The next rising edge is our input is at 0, and our enable is at 0. So since we prioritize the enable, we're gonna keep it as 1, even though our input is 0. So we're gonna move on to the next rising edge, which is our last one. And for our last rising edge, we have the input 1 and enable 1, so we just keep 1 again. And that's how you do this one. Do you have any questions? Okay, so let's move for another practice. This one is a little bit more complicated. We have a clock, we have A, which is the input, we have reset, we have load 1, load 2, and we have 2 outputs. So for this one, we're gonna, as always, look at reset. And For the outputs, and we know that the reset is 1 at the beginning, but first we always start with the unknown, right? So for this one, since we're using letters, since it's unknown, we usually use question mark. So we'll have question mark for B. And let's do for B first, and then once we do B, we're gonna go look for the output C and solve for it. So looking at the reset now and this rising edge, we see that it's at reset is on, so it has to be a 0. And we'll be moving on to the next rising edge. Next rising edge, we're gonna look at the input. We see that input is 8, reset is 0, so we're good to go. And load 1 is at 0, which means that we're gonna stay with 0 and we're gonna ignore the 8 for B. And then we're gonna go to the next rising edge, this one, and we're gonna look at reset 0, so we're good to go. We're gonna look at load 1 is still at 0, so we're just gonna ignore the 4 and we're gonna move on. And now we're gonna put a 0 on your output, and you move to the next rising edge. Let's look at the reset's still 0. Load 1 now is at 1, which means that we're not gonna ignore the letter here, which is D, and we're gonna use it as our output. So our output for this one has to be D. Oh, sorry, that's supposed to mean a D. And let me just double check I didn't do anything wrong. 1, we have it's at 1, so D should be our output. Yes, everything looks good. So let's move to the next rising edge. Next rising edge, we have C, reset 0, so we're good to look at L1. And L1 is at 0, because we see this part here. It's at 0, so since L1's at 0, we're just going to keep the previous output like we've done here. We had an example here that even though our input was 1 here around this area, but our enable was 0, so we kept the output as a 1. So we're gonna use the same concept in this question. So we're gonna keep the D. That's a D. Oh, sorry, that's a D. And we're gonna move on to the next rising edge. Next rising edge, we have reset. Reset's at 0, so we're good to look at load 1. Let's look at load 1. Load 1 is a 1. So now we're gonna use the number 0, which is on the below the clock, the rising edge. So 0. And we're gonna move to the next rising edge. And for the next rising edge, we look at the reset. Reset is 0, so we look at the load 1 again. Load 1 is at 1, so we're gonna use the new input now, which is 3. And then we're gonna look at our other rising edge. Our rising edge is at 0. It's below 0, so we're gonna keep the 3. And our reset's at 0, so we're good to go. So we keep the 3 because our input is at 0, so we gotta keep the previous number. And we're done for B. We finished B. Now we're gonna move on to by the way, do you have any questions? Okay. We're gonna move on to output C. And let's start again. So reset, or first we're gonna start with the question mark, right? Because the first one is unknown. And we're gonna look at the first rising edge again. So let's look at L2 now. L2 is at 0. So we're gonna have a 0 as our output. We go to the next rising edge. Our next rising edge has an 8. We look at the L2. L2 is at 1 now, so we're gonna put a 8 here because that's the input we have, and we're gonna move on to the next rising edge. This one, it's a 4 now, and we look at oh, sorry, I forgot to mention, but you always have to look at reset. If reset is ever at 1, you're gonna use a 0 because that's gonna reset everything. So you guys gotta keep that in mind because we prioritize reset over everything. And let's go back to it then. We're at the third rising edge, and that's 4. Let's look at our L2. L2 is at 1, so we're gonna use that output or that input, sorry. And we move on to the next rising clock. Our next rising clock, our L2 is still at 1, so we're gonna change the input again. This time it's a D, so we put a D, and we move on to the next rising edge, which is this one, C. Reset 0. Reset's gonna stay 0, so we're not gonna have to worry about it anymore. But we do have to look at L2, and L2 is a 1, so we're gonna put C here, which is the input for that rising edge. And we're gonna move on to the next rising edge, and let's look at L2 now. L2 is 0. So because L2 is 0, we're gonna keep C. Yeah, we're gonna keep C because remember, once the load is at 0, you keep the previous output. So once we finish that, we're gonna move on to the next rising edge, and we're gonna look at load 2. Load 2 is at 1, so we're gonna use that input, which is 3 right now, and we're gonna go to the last rising edge. Last rising edge, we look at the load 2. Load 2 is at 0, so we keep the 3 here, and that's how you do it. Do we have any questions about this? We're good? Okay. Yeah. Now let's move on to memory. So I put a first slide here just to go over about memory because it's more of a conceptual topic, and we have two main type of memories, which is RAM, random access memory, and it can read and write. Keep that in mind because that's really important. While ROM, read only memory, it reads only, and it is also a programmable logic device. And the way I think about the problems is that I keep in mind that RAM has register files, DRAMs, SRAMs, and they only work with battery. If power is lost, these will not be working. While ROM, if you have power, or if you don't, the memory will. Sorry, let me rephrase this. If you turn off, if power is lost for RAM, memory will not be contained. While for ROM, if power is lost, you will still keep that memory that you had before. So keep in mind that register file, DRAM, and SRAM are RAMs, and they need power to store the memory. And ROM, it has more components, which is EEPROM, EEPROM, Flash, and Mass Program ROM, and OTPROM. These are the the ones that if you don't have power, you can still have memory stored, and it will not be lost. So let's practice with these because these are tricky. So the way I like to do them, I like to read the questions, and based if the question is pretty simple, then I would I will choose what it is. But if it's a question that it could be multiple answers, I just move to the next one, and I figure out the others, and then whatever is left, I kind of use it because it makes it easier for me. So let's start with the first one. A manufacturer of small quantities of microcontroller needs to permanently program the firmware. So this one, uh, we can look at it. Let me think about it a little bit. This one, it has a small quantity of microcontroller that needs to permanently program the firmware. Look at this. This tells us that it gives an idea of something that's unique. And when I think about it, we know that OT-PROM stands for only time programmable ROM. So we know that's it's a only one time reprogrammable. So once you program it, you can't reprogram it again. So this will have to be OT-PROM. I think it's pretty obvious. And when we go to the next one, it says cell phone firmware is a large amount of code that must not be lost when battery dies and must be easy for the phone company to upgrade. So right off the bat, we know uh, that uh, so we know that the memory will not be lost when battery dies, right? Because it tells us right there. So we know it will be a ROM memory, and it has a large amount of code. And this one, uh, I think it's Flash because Flash can it can hold a lot of data, and it is the one that can hold the most data, and it's easy for the phone to company to upgrade. So I want to say this is Flash, but let's keep in mind that we could go back if we sorry let me rewrite this. Sorry. Oh, sorry. OT prom and Flash. So let's keep in mind that we could still change this, but it looks like it's gonna be Flash. And let's move to the third one. When turned on, a talking teddy bear mimics what a child says to it after a short delay. Then it forgets what it heard. The bear is capable of learning a 10-second phrase sentence and repeating it back, but it doesn't retain it. So this one will most likely be RAM since it doesn't retain information. Uh, it indicates that when the when the power is turned off, memory will not be stored, and it looks like to me that it is SRAM because SRAM cannot store much much memory, and this one can only hold a phrase for 10 seconds. So we'll start with SRAM plus yeah, I think this will be SRAM because it doesn't store as much energy, or sorry, as much memory, and it it looks like it'll be a RAM memory. And then we have this is a very simple one because it says this type of memory was very popular in the 1980s, but it's not used as much today because newer types of memory are easier to reprogram. And this one is the E EEPROM or EEPROM, sorry. Whenever you see something talking about the 80s or something about in the past, you know that it is EEPROM because EEPROM is the older version of these memories, and you can kind of associate that with EEPROM. Let's move to the next one. A portable keychain device stores 256 phone numbers. Each number can be reprogrammed by a few button clicks. So this one, it says that each number can be reprogrammed by a few button clicks. So it implies that you can change the number, but it has to be one at a time, from what I read. And from that information, we know that it has to be EEPROM, because EEPROM can only change one number at a time. It cannot change everything, include like all of the numbers together. It has to go one at a time. It doesn't have the ability to do everything together. Let's go to the next one. Large amounts of data, big data, are placed in this type of memory while it is being analyzed uh, to uncover previously undiscovered patterns. Large amount of data. So we know it's a large amount of data that it's placed in the memory while it's being analyzed to uncover previously discovered patterns. Let's wait on this one for now, and we'll go back to it. So, RFID tags contain a memory and a transponder, which allows the memory to be read by an RFID. The reader contains the only power supply for the system. A tag's unique TID, tag ID, hashtag uh, is selected and stored by the manufacturer. It cannot be changed. So this one, it has to be a mask from, and the reason for that, it is because we we have it's the code cannot be changed, and it's producing a big a big amount of it, because it says contains a memory transporter which allows the memory to be read by an RFID reader. The reader contains the only power to supply for a system. A tag Unix is selected and stored by the manufacturer. So this one will actually be I erased this one by mistake. This one will actually be OT-PROM, because sorry, I erased the wrong one. EEPROM, OT-PROM, because it's unique and it cannot be changed. So this is the OT-PROM. And then sensors in an airplane monitor engine conditions and store the data in local memory. The pilot reviews the data by reading it from the local memory. Data is lost when the engines are shut down. So on this one, we can see that it's doing multiple things at a time. It's writing and it's reading. So and it also says that when data is lost, the engines are shut down. So we know that it has to be RAM, and since it's doing multiple things as writing and reading at the same time, we know that it has to be a register file, because register files are the only ones that can do that can read and write at the same time. So let's go back to the previous ones. This one, since it says large amounts of data, big data, are placed in this type of memory while it is being analyzed to uncover previously undiscovered patterns. Uh, since we've used all of the other ones and we're missing DRAM and mask, we know that large amounts of data are usually associated with DRAM, because DRAM has more memory to store. So this one will have to be DRAM. And the first one, let me think about it a little bit. We have mask PROM, and and we have we're gonna put max prom here, but RF. I just want to look at the RFID again and the mass prom because I'm just trying to figure out which one is gonna be OT prom and mass prom. But those we can see that they have patterns that it says that the program will be only it will only be programmed once. So we gotta look carefully at those. Manufacture of small quantities. Microcontroller needs to be program. Memory, the FDI contains memory to memory to be power supply for the system. Not be changed. Yeah, so Varsha, can you come here real quick? I'm not sure. I'm trying to decide if this is OT prom or if this one will be OT prom because they both talk about being programmed once.
Mm-hmm.
And double check. Yes, so I was right at the beginning, but this will be OT prom. And sorry, I erased the flash. And then the second to last one will be mask. Sorry, I erased the DRAM. But
Yeah,
I just want to give a good explanation because mask it usually says that it's similar to the OT prom, but it is produced in large amounts, right? So this one says small quantities. That's why and it says program the firmware. So this one has to be OT prom, and like it makes sense because it's small quantities and it's unique. It's only programmed once. But I don't see here where it says that it the RFD tags contain where it says that it's produced in a large amount, but I think we should assume that our RFID tags are produced in a large amount.
Yeah,
So
if it doesn't tell you that it's a small quantity, you can just assume that it's being mass produced.
okay, so as Varsha explained, we know that RFID tags are usually mass produced, so uh, we had to use that assumption, and from that assumption, we know that it has to be a mask programmed ROM. So that's the reason. Let me just fix the RF here. So let's move to the next practice, and let's read it. A vehicle audio unit contains a memory with unique security code that cannot be changed. Your vehicle audio unit code should be your owner's manual. So we can see that this vehicle audio unit contains a memory with unique security code that cannot be changed. As we said before, this will have to be OT prom, right? Because it's only for the car. So it's only for the car, so it's a small quantity, right? It's only one, and it cannot be changed. So it's a one-time programmable ROM. Let's go to the next one. A digital photo frame holds up to 32 photos, which can be uploaded by the user and changed at any time. The frame displays a different photo every minute. So, uh, 32 photos. Uh, it's a it's gonna be a ROM, and it's gonna be a ROM because it's you can see the frame displays a different photo every minute, and that indicates that it's kind of slow, and we know that ROM is slower than RAM, so we can assume that this type of memory is ROM, And to decide which ROM memory it is, we can look at this part, which can be uploaded by the user and changed at any time. This shows that the type of memory has a ability to do a lot of stuff and it's practical. So we should probably stick with flash for these reasons and move on to the next one. A car radio can be programmed uh, to select the driver's favorite stations, but the programming is lost if the car battery dies. So with this hint that says that if the car battery dies, we know it's RAM, and now we just have to decide which one it is. And so since the car radio can be programmed to select the driver's favorite stations, uh, it indicates that it can store quite it can store not as much information as like normally like normal things. So the out of the three RAM memories, we know that SRAM is the one that can store the least memory. So we'll stick with this one for now. We're gonna move to the next one. When a popular children's doll hand is squeezed, she repeats one of the three pre-recorded messages. This one will be ROM memory because uh, it doesn't it doesn't have power. The children doll hand doesn't have power anymore, but it still uh, display the recorded messages. So with that in mind, uh, we know it's ROM, and I'm uh, I'm gonna say um I'm thinking that this should be mask because let me write mask because uh it says popular, and by popular we know that we can infer that it is mass produced. So we're gonna stick with mask for this one, and we're gonna move to the next one. A video gamer relies on this type of memory to maintain the current picture in his/her video game while she's playing. Okay, let's look at this. It says that he relies on this type of memory to maintain the current picture. So we can right off the bat we know that it's RAM, and we use SRAM, so we know it won't be SRAM, and it it requires quite a bit of memory to be storing to like maintain all of the information that a video game has, and DRAM is the type of memory with the most memory that can hold the most memory. So we're gonna stay with DRAM. And for the next one, a portable device stores the name of active club members. Names may be individually added or removed using buttons on the device. This one, I think it's pretty obvious. It should be oh, sorry, E pro. Sorry, let me fix it. DRAM. This one should be, excuse me, EEPROM because uh, because of this key sentence. Names may be individually added or removed by using buttons on the device, and that's an indication of EEPROM memory because whenever you see it, if you have it on the test, whenever it emphasizes that it's individually added, individually modified, or something, it's most likely gonna be EEPROM because that's a pattern of EEPROM because it can't do multiple things. It can't change multiple things at the same time. And the next one, I just saw the keyword in the 1980s. and we know it's EEPROM. So, like I said again before, when you see so used by an engineering student in the 1980s, you can just assume that it will be EEPROM because that's the that's what they use to normally identify the EEPROM as one type of memory. And the last one, it's the only one left. It's register file, but we can also look at it and see that it is register file. A small memory in a truck holds data sent to it from sensors under the vehicle's hood while the truck engine in running. The vehicle occupants can dial through the data to check current readings of mileage, exterior temperature, and estimated miles remaining on the current tank of gas. So right here we see that it's a small memory, and it shows that engine is running. So we when it talks about engine, about power being power on, we know that it's RAM, and when it's a small memory, we know that it won't be DRAM because DRAM is the largest one. Now we just have to decide between register file and SRAM, and we can see that it holds the data from sensors, and it can also dial through the data of check uh, checking current readings. So we can see that it's writing and reading at the same time, doing those at the same time, and that's an ability that SRAM doesn't have. So this one has to be register file, and that's done for memory. It's a kind of a tricky topic, and sorry about the mistake early on. And do you have any questions about it? Okay. So
Sorry, one thing I'd like to add is that a lot of these examples, they tend to repeat even on the exam. If you get familiar with how to analyze them, like Kawan just explained, you'll be able to like pattern recognize for the exam itself.
okay. Yeah, so now we're moving on to the registers. I got a couple of notes for y'all. So first is just located in the CPU. It holds data and addresses. Register files has 32 registers, and each of the registers, the small registers, like these can only hold 1 bit. So let's go to practice. So this one, it says that we have to write 821, and it wants it in binary, or sorry, binary and hex. So there are multiple ways you can convert decimal to binary, but I like to add numbers because I just find it easier for me. But you can stick to your method. So we'll start with 512 because that's the smallest number before we can use 1024. So we'll start with 512 plus 256, and that's 512 plus 256 is 256 plus 32. Sorry, let me write it. Plus 32 plus 16 plus 16 plus 4 plus 1. So that's 821. And the way we write it, we look at the numbers we have. We have 1 here. After 512, we're gonna go to 256, and it's a 1. Then it's after 256, it's 128. So we don't have 128, so it'll be a 0. We don't have 64, so it would be a 0. We do have 32, so it'll be 1. We do have 16, so 1. We don't have 8, so 0. We do have 4, so it'll be a 1. We don't have 2, so 0. And we have 1, so it'll be our binary will be 1100110101. And from there we're gonna convert that into hexadecimal, and that's 5 because we have a 1 here. Nothing for 4, or nothing for 2, and a 4. 4 plus 1 is 5. And we have 3 here, because we have a 1 here, 1 here, 1 plus 2. It's 3. And we have the last two numbers. If you don't have 4 digits here, you just add 2 zeros just to complete it. And you can see that that's a 3 because it's 2 plus 1, so 3. So our hexadecimal number, which is what we're gonna put in our W data, is 1 second, let me erase this. Is 335. And we're writing the 821 into T7. So T7 in the registers, if you remember, we have T0, T1, T2, T3, T4, T5, T7. And the way you write it, you simply write it according to the number. And we know 7 equals 1, 1, 1, because that's 1 plus 2 plus 4. So we're gonna write 1, 1, 1 for W address, and we're gonna write zeros here, these, except for D7, which is what we're writing to. And our enable should be, or right enable should be 1. And let's look at what else we're doing. We're reading the contents. Let me just erase this to do the rest. We're reading the contents of T2 at read port 1. And we're reading the contents of T5 at read port 2. So let's start with read port 1, which is T2. We're writing T2, we're reading T2, sorry. And that's 5,974. And let's convert that into binary, which is what they want first. So we start with the closest number will be 4,512. We go to 512 times 2,024 times 2, 2,048 times 2, 4,096. That's the smallest number we can do before 5,974, and plus 1,024 plus 512 plus 256 plus, let's try it, 128. No, that's too much. So we do plus 64. 5952. Oh, sorry. Plus 64 plus 16 plus 8. No, that's too much. So plus 4. And then plus 2. So let's write that in binary now. 1,096, we have it. We don't have 2,048, so it'll be 0. 1024, we have it, so it'll be 1. 512, we have it, so it'll be a 1. 256, we have it, so it'll be a 1. We don't have 128, so 0. We have 64, so 1. We don't have 32, so 0. We have 16, so a 1. And we don't have 8, so we'll write a 0 here. And we do have 4, so we'll write a 1 here. And we'll write a 1 for 2 and a 0 for 1 because we don't have 1. And now we're going to convert that into hexadecimal. So split it into 4 numbers. Let me just rewrite this, make it better. Oh, sorry. Let me just rewrite everything and spaced out so you guys can see better. So 1, 0, 1, 1, 1, 0, 1, 0. Sorry, let me 1, 0 for 2000, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0. Okay, we're back to it. So let's write this number in hexadecimal. So this is a 2 plus 4, 6. This is 1 plus 1 plus 5, 1 plus 4, sorry. It's a 5. We have a 7, and we have a 1. So that's what we're going to write into R1. 1, 7, 5, 6. And we're reading that into D2. So D0 is going to be 0. D1 is going to be 0. D2 is going to be 1. And the rest is 0. And since we're reading here, our R1 is going to be 1. And just to be safe, I like to write the number that we're reading into T2. I don't think it's 100% required, but you can do it just to be safe. Just write it here. And after that, you're gonna write your read address. So since we're reading it into T2, our read address has to be 2. So we just write 2 in binary, which is 1 0 or 0 1 0. Sorry, 0 1 0. That's our read address. And now we move to the read 2, which is the last one. And we're reading port 2 at T5. You have let's just do the easy parts first, and then we're gonna convert it to a hexadecimal. So since we know we're reading at T2, or we're reading at 2, port 2, we're gonna put a 1 for R2 enable, and we're reading at T5, so we're gonna put zeros everywhere other than D5. And we know that 5 in binary is 1 0 1, so we can also write that in our read address. 1 plus 4 5. And now let's go to the longest part. Let's convert T5, so T5 is 58, into binary first, which is what they're asking for, and then from binary we go to hex. And this is an easier one because it's a smaller number. So 32 plus 16 plus 4. Let me just double check my calculator. 32 plus 16 plus 4. Yes, sorry. That's not 58. 32 plus 16 plus 8 plus 2. Okay. Plus 8 plus 2. That's 58. And you're gonna convert that into binary. So 32, we have a 1, 16, we're gonna put a 1, 8, we're gonna put a 1, we don't have 4, so it's a 0, 1 for 2, and then a 0. Now we convert that into hexadecimal, so we'll split it in groups of 4, and this is 2 plus 8, so 10, and keep in mind that 10 is A in hexadecimal. 10 is A. I'm just gonna put the list real quick. 11 is B, 12 is C, 13 is D, 14 is E, 15 is F. Just keep that in mind, because if you write 10 instead of A, you will lose points. So we have A, and we have 1 plus 2, so 3. So our read data will be 3A. And you can just write your your number here just to be safe. Uh, in the load, just to be safe. If you want to, I never seen on the test when I took it. It wasn't required, but you can write it there if you want. And sorry, let me just correct myself. It should be T2 right here. It's not in binary. It's gonna be 5,974 and 58 at T5. So now let's go to the last question that we have on the register, and this is a simpler one. It just has a write and a read, and we're writing 742. We're writing that into T0. So let's go to our W address. We know T0 is just 000, and D0 will be 1, and the rest will be zeros. The rest will contain zeros. And our write enable is 1. So let's convert 742 into binary. So we have 512 plus 128. 128, that's 640 plus 64 plus 32 plus 4 plus 2. Okay, that's 742 if we add all of these up. And that's 1, because we have 512, 256 we don't have, so it's a 0. 1 for 128, 1 for 64, 1 for 32, 0 for 16, 0 for 8, 1 for 4, 1 for 2, and 0. So let's convert that into hex. Split it in groups of 4. We have 2 plus 4, 6. We have 2 plus 4 plus 8. 2 plus 4 plus 8, that's just 14. That's going to be E, because 14 is E. And we have 2. So our write data will be 2E6. And now we look at the read. We're reading contents of T4 into the report 1. So let's start with the nice and easy stuff first. Since we're writing at T4, we're gonna have zeros all around except for T4. Our read enable is gonna be 1, and our read address is T4. T4 is just 100, because that's 4 in binary. And now we have to convert T4 7,412 into binary. So let's start. 4,096 plus 2,048 plus 2,048 plus 1,024 plus 256. That's too much, so not 256 plus 128 plus 64 plus 32 plus 16 plus 4. Yes, that equals to 7,412. So now we write that in binary. 4,096 we have it. So it'll be 1. We have 2,048 1. We have 1,024, so it'll be 1. 512 is a 0. 256 is 0. 128 is 1, 64 is 1, 32 is 1, 16 is 1. We don't have 8, so it's 0. We have 4, so let me double check if it's 4. Yeah, it's 4. So we have 1 and 0, 0. Let's convert that into hex now. And that'll be, we have 4 here. We have 15 here, because that's so let me back it up. So that's a 1 plus 2. There's no 1, there's no 2. It's only a 4, so it's a 4. We have a 15 here, which is F. And we have a 1 at the end. And over here, we just have a C, because that's 12. So, or read data will be 1CF4. And that's all we have to do for this register. You could write the read number into T4 if you want. So it'd be 7,412. But that's up to you. And we're gonna start part 3 now with Varsha.
Okay, so part 3 is going to cover some of the binary arithmetic stuff. Information as bits, floating point, and fixed point notation. As a reminder, you will have some questions about whether a number has overflowed or underflowed. And the way you can determine that is if it's within a certain range. When you have unsigned binary numbers, so anything that's positive, this is the formula that you would use to figure out what the range that you can represent is. So let's say, for instance, if I was looking for the range that can be represented by an 8-bit binary number, you can go from 0 to 2 to the 8 minus 1, which means that you can represent any value from 0 to 255. One second, just grab my calculator. Okay. When you have signed numbers, with, let's just say, the same n is equal to 8 bits, your range is going to be different because you have to represent both negative and positive numbers. So what you have, I'm going to put my negative sign here, 2 to the 8 minus 1, all the way to positive 2 to the 8 minus 1, which means you can represent numbers from 2 to the 7. So that's negative 128 all the way to positive 127. And the way you can double check that this is the right range is there should be 255 numbers in between these two, which should tell you that you can represent at any given time with 8 bits 255 numbers. The cases when you have overflow or underflow. Overflow is when your number is too large to be represented in a number of bits. So let's look at an example down here where you have 4.01. This is the full binary equivalent representation of it. Remember that the number 4 requires 3 bits to represent. The number 0.1 is roughly 8 bits. So let's say 8 bits here, and this requires 3 bits. When you are representing it in fixed point notation, which we'll go over in a slide, but let's say if you have Q 4.2, that means you only have access to 2 fractional numbers, leaving 2 integer values behind. So this is how you would represent 4.01 with that notation. Because you only have two bits in the integer portion into the fractional, you cannot represent 4.01 because 3 exceeds the 2 bits you have available, as does 8. So in this case, this binary representation has both overflowed and underflowed. Questions? Okay. So we'll just go over these examples really quickly. In this question, you are told that you have 8-bit unsigned numbers, and you have to determine whether these numbers will produce an overflow. Generally, you could just add these numbers up with decimal values, and you should be able to say whether it overflows or not. If we remember from up here, we're going to use a formula for unsigned bits. So you can represent 0 to 2 to the 8 minus 1, which means you can represent anything between 0 and 255. So when you add 78 plus 145, you get that the sum is 223. 223 is less than 255. So you're okay. You can represent it within the 8-bit within the 8 bits. So if I were to add 149 and 116, you get that your sum is 265, which is greater than 255, which means no, it cannot be represented and it overflows. Though this doesn't specify that you should add them in binary, if you were to add in if you were to convert to binary and add the numbers together, you will see that you have an extra overflow bit once you sum them together. Let me write that down. You will see an extra bit, which will also indicate to you that it has overflowed. But this is the fastest way to tell by comparing the sum to the range. And if they were to give you 9, 10, 11 bits, you would do the same process. So for part C, this is the same as we've done before. This asks for the largest unsigned number you can represent with 6 bits. So let's put it into our little formula. It's 2 to the 6 minus 1, which gives us 63. So that's the largest number. And as just for reference, you can represent 0 to 63 with 6 bits. And then for comparison purposes, what is a range of signed numbers? We can represent using 2's complement. So if we put it in our formula for signed numbers, we have 2 to the 6. Let me go back to here. Remember, 6 minus 1. 2 to the 6 minus 1, I believe. No, 2 to the 6 minus 1 minus 1. Okay, so that means negative 2 to the 5 to 2 to the 5 minus 1. So I can represent negative 32 to positive 31. And if I were to look at how many numbers are between these two numbers, it will actually be 63. Okay. I know you've all practiced a little bit of decimal to hexadecimal conversions, but this chart, or this slide is just to remind you that when you are converting from binary to hex, you group numbers by 4 bits. If you're converting binary to octal, you would combine the bits by 3s. And then when you're combining, sorry, I keep saying combining, when you're converting from decimal values to binary or hex or octal, you do a divide by 2, by 16, or by 8, and you keep dividing until your remainder is 0. In the case of where you're converting a fraction, so something that's like 0.625 to binary, hex, or octal, you're going to keep multiplying it until the product is 1. We're going to have an example of it on the next slide, or 2 slides after, actually. And this slide is to remind you that the range for binary numbers are just 0 to 1, but the range for hex goes from 0 to 15, where our double-digit numbers, so 10 through 15, is represented with letters A through F. It always helps to just write these down on your cheat sheet or somewhere in the corner so you can remember what the decimal value for each of these hex values are. And then lastly, for octal, your range is going to be from 0 to 7. And as with both hex and octal, once you go past a certain range, you loop back. So if you were to try to represent 8, you would actually loop back to 0. Because you only have 3 bits available and you cannot represent anything larger than the number 7. Okay, so let's do these 2 examples really quickly. From this notation, you can tell that this number is given to you in hex. Other representations you would see probably would be this 0x 3b4 point D. Both of them are equivalent representations. So the first thing it tells you is to convert it to binary. Remember that hex has 4 digits that are represented in binary. So if we had to represent 3, you have 0, 0, 1, 1. The letter B is actually the value 11. So if we had to represent 11 in binary, it's going to be 1, 0, 1, 1. And then peek over there. Yes, that's correct. 4 is represented as 0, 1, 0, 0. And then the letter D is 13. So our binary equivalent is 1101. So I'm going to write this as 0011, 1011, 0100.10, nope, 1101. Okay, so if we had to convert this to decimal, you could do it one of two ways. You could take each of these binary numbers and then multiply them by the 2 to the whatever value, right? Or you could go from hex to decimal. So let's go from here. So hex conversions to decimal follow the same rules as binary. So we're going to say this is 16 to the 0, 16 to the 1, 16 to the 2, and over here 16 to the minus 1. So we do 3 times 16 squared plus 11 times 16 to the 1 plus 4 times 16 to the 0. Decimal d is 13, 16 to the minus 1. When you put this all together, putting it in my calculator, 4 times 16 squared times 16 plus 4 times 16 to the 0. Get that this is 948, and then decimal 16 to the negative 1. 948.8125. And you're going to represent that in with a little subscript 10 because that's how you represent decimal numbers. Yes. And then all of this you can represent with a little subscript 2 if it's not obvious that it's a binary number. So for part C, we're converting hexadecimal to this binary value to hex and then decimal. I'll just do the hexadecimal part. I trust that y'all can do the binary part. But we're going to go through and group these by 4 digits each. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So we have, let me write this down. 0, 0, 1. 1, 1, 1, 0, decimal 0, 1, 1, 0, and then 1. So in a case where we have a single bit, or even if there's like 2 bits, we're going to 0 pad it. And we're going to add leading zeros or trailing zeros depending on whether it's a integer number or fractional. So once we add those trailing zeros, we're going to just assign these hex equivalent values. This is 5. This is 14, so that makes it E. Let me double check. Yes. This is 6, and this is 8. So the hexadecimal equivalent of this binary number is 15E.68. And we'll put, we'll put a little subscript 16 next to it. Then you can convert it to decimal either from binary or from hex, whatever feels more intuitive. Okay, let me just write. Okay, questions? Okay, fabulous. So we're moving on to our 2 methods of representing fractional values, or just any binary value. The first one is fixed point notation, where you're given something in the form of q n dot f, where n is the total number of bits and f is the number of bits that you have in the fraction portion. Basically like the decimal value, but decimal also means base 10, so they said fraction, not to get confusing. But general steps are when you're given a number, it could be 14, just generally 14, and you want to you have to convert it to a binary value. From there, you can add fractional bits because 14 is represented easily by a 5-bit binary. And then because you are asked for 3 decimal values, you're just going to pad it with zeros after the decimal. I'm going to do an example next so you can see what it looks like. And then our next form of representation is floating point or IEEE notation, where you are going to represent any number in 32 bits. The difference between fixed point and floating point, aside from one is a small number and one is a gigantic one, is that floating point represents everything from signed to unsigned numbers and also represents both fractional and integer values the same. So general steps for floating point representations are that you convert any given number into binary first. You're going to write it into scientific notation. It's important to note that once you convert it to a scientific notation, there is a 1 that's before like the fractional portion. That value is implied and doesn't make it into the final floating point like IEEE number. And then your sign bit's also converted. You bias the exponent, and then you put it all together. So it's a lot of steps, but let's work through it. Let's work through one of them. So the first one is going to be converting this decimal value to Q8.3 format. So in terms of steps, let's write this down. 19.5625. First thing we're going to do is convert to binary. So I'm gonna do a little division here. So 19 divided by 2 is 9, leaves you a remainder of 1. Well, 9.5. And then 9 divided by 2 leaves you with 4, remainder of 1. Oh no, I'm running out of room. Okay, 4, this is divided by 2, gives you a remainder of 0. 2 divided by 2 is 1, remainder of 0. 1 divided by 2 is 0, remainder 1. So remember I said you keep going until your remainder is 0. That's when you know you can stop dividing. So then let's convert the 0.5625 into binary as well. We're going to do this by multiplying it by 2. Let's see, 0.5625 times 2. You get that it's 1.125. From there, you take this fractional portion and you keep multiplying it by 2. So 0.125 times 2 is equal to 0.5. 0.5 times 2 is equal to 1.0. And we can stop because we've reached a 0 as like the fractional portion. So when we're putting this value together, for integer values, you go from the bottom up. So your answer is 10011. And then for the fractional portion, you go from top down. So I'm going to put .101. We can do a quick check to make sure that this is actually 19.625. So this is 2 to the 4, 3, 2, 1, 0. 1 second. 2, 1 plus 2 to the 0. Yep, that's 19. And then 2 to the minus 1 plus 2 to the minus 3 is 5.625. Oh, did I mess up somewhere? No, I think that's good. Okay. So once you have your binary number, you're going to put into the Q 8.3 format. So actually, this is perfect. I'm going to change this to say Q. Let's just go like 6.2 or something, so we can see what happens to your number. So this means that you have 6 total bits to represent it. 2 of them have to be your decimal portion or your fractional portion. So let's keep the 2 bits after the decimal, which means we have 4 of them left to begin with, 0011, and this is your final answer. This is an example of both overflow and underflow because the greatest part of your number has been chopped off and so has the smallest part. Okay? Okay. So for this example, for converting negative 25.625 to IEEE format, the first step is convert to binary. Okay, so going to assume that you all know how to convert to binary for now, and then just tell you what the what the binary value is. Where did it go? Okay, so the binary value here is going to be 11001.101. Okay, and then the second part is convert to this is called scientific notation. Scientific notation. Okay, so we have 11001. 101, so we're going to move it 1, 2, 3, 4, which means it'll be 1.1001101 times 2 to the 4th. So remember I said that this one is going to be implicit, meaning it doesn't make it into your final IEEE notation. So we're going to take this as the fractional bit here. And then the third part is going to be by its exponent. So what we have is, we take this 4 up here, 4 plus 127, which means you get 131. You're going to convert the exponent, convert to binary for an 8-bit binary number. So 131 in base 10 to an 8-bit binary number is 10000011. Okay. And step 5, we're just going to put it all together. Put it all together. There we go. Okay. So the first bit in IEEE format is going to be our sign bit. because this is a negative number, the sign bit is going to be 1. If this was a positive number, it would be 0. Okay, wait, let me write this here. Then we're going to put together our exponent, which is 8 bits, which is the one here, 1, 0, 0, 0, 0, 0, 1, 1. That's our exponent bit. And then we're going to do the rest of our floating point value. So this portion here, the one after the decimal, is the one that we're actually including. So we have 1, 0, 0, 1, 1, 0, 1. Because again, this is implicit, it's not going to be included. And this floating point value has to actually be 23 bits. We've only got 4, 7 here, so we're going to add zeros until we get to 23. So only keeping countable. So this is 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Ideally, it's all in one line. But I'd recommend that when you're writing this down, you be very careful that you have not dropped a 0 here and there, because this whole number, when you count up all the bits, has to be exactly 32. I'm going to assume it's 32 for the sake of time, but don't do that in your exam. Okay, so this one is we're converting it from when you're given a 32-bit binary number into decimal. The first thing you want to do is just break this up. So then the 1 here means that it's a negative sign. That and then this number here is your exponent bit, right? So let's write this value in, I believe this is 132. Remember that we bias the exponent when we're converting to IEEE format, so we have to unbias it, which means that we subtract 127 from it, which gives us 5. And this 5 also tells us that we are taking 5 from these, from the first bits of like this 23-bit number. So we're going to put the negative sign here, and remember that we have to bring back that implicit 1. Let me put it over here. So this 1 is implied, right? So we're going to put the 1 decimal mark. We have 1, 1, 1, 0, 0. And then we're going to write 2 to the 5. In order for us to get this into a proper binary number, we're going to remove the scientific notation, like move the decimal over. So 1, 2, 3, 4, 5. So we have 1, 1, 1, 0, 0. I'm going to put the negative sign up front. And you're just going to figure out what the value of this in decimal is. So when you do that, you have 2 to the 0, 1, 2, 3, 4, 5. 2 to the 5 plus 2 to the 4 plus 2 to the 3 plus 2 to the 2, which gives us plus 2 to the 3 plus 2 to the 2, 60. I believe I got that right. Yep. Okay. And then remember, don't forget about the negative sign. So your final answer is negative 60. Okay. Questions? Okay, fabulous. Let's go into binary coded decimals then. This may seem a little tricky, but the important thing to remember is you add up, you convert each digit to its binary representation. Binary rep, not each two. Then you add each of them, add bitwise. And then if your sum for those like group of 4 bits has exceeded 9, if let's see, if group of 4 is greater than 9, then you have to add 6 to it, 6 in binary. Okay, so we're going to see that. So let's see, we have 7, 4, 9, 6, then 4, 3, 5, 8. And we're going to add those together. So let's work on converting each of these to a 4-bit binary number. So 7 is 0, 1, 1, 1. 4 is 0, 1, 0, 0. 9 is 1, 0, 0, 1. 6 is 0, 1, 1, 0. And then on our next row here for 4, we have 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 1, and then 1, 0, 0, 0. I think I said that many. Okay. So now we're going to do bitwise addition. 0 plus 0, 0. 1 plus 1 is 1. Sorry, 1 plus 0, 0. Here, 1. 1 plus 1 is 2, which in binary is represented as 1, 0. So this is your sum, and this is your carry. I'll write that over there. So 0, carry the 1. Add this 1, add the 1, add the 1. 1, 1, 1, 0, 1, 1, 0, carry the 1, and sum. Okay? So, so we've done parts 1 and part 2. So in part 3, we're going to check if each group of 4 is greater than 9. So remember that 9 is 1, 0, 0, 1. Okay, so this value is greater than 9, so we're going to add 1, 0, 0, 1. This value is equal to 7, not greater than 9. We don't really care what happens to it now. This third number is greater than 9, 0, 1. And then we're going to add 1, 0, 0, 1. And then we're going to add bitwise again. So when we add this together, you have 1, 1, 1, 0, carry the 1, 0, carry the 1, 0, carry the 1, 0, carry the 1. You have 1, carry the 1. So it's 0, carry 1, 0, carry 1, 0, carry 1, bring down the 1. And then over here we have 0, carry 1, 0, carry 1, 0, carry 1, 1, and then we have an extra bit here. It's important to note that for binary coded decimals, you do not discard your overflow bits or like this extra number here. What you're going to do instead is you're going to add a couple zeros in front of it. So your final sum here is 0, 0, 0, 1. Okay, I think I messed up on the addition somewhere. Give me a second. Oh, shoot, okay. Hang on. Sorry, I know what the answer is supposed to be, and I don't think I've added these right. 1, 1, 1, 1, 1, 0, 1, 1, 0, 0, 1. Okay, and then I said add 9 to each of these. Oh, shoot, that's what it was. It was add 6 to each of these. So if greater than 0, there we go. Okay, don't make that mistake on your exam. 0, 1, 1, 0. Okay, there we go. Okay, now we can add properly. 1, carry the 1, 0, carry the 1, 1, 0, carry the 1, 1, carry the 1, 0, carry the 1, 0, carry the 1. And then this was 1, 0, carry the 1, and then 1 up front. Okay, perfect. And then we're going to pad this with 0, so we get 4 numbers. So our final answer for this is 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0. The quick way to check if you've done this correctly is by adding this in decimal. So if I did 4 plus 1 plus 6 is 14, this is 15. 5, 3, 8, this is 11. So these numbers exactly have to match up to the ones that you've got here. So this value is 1 in decimal, this is 8, this is 5, and this is 4. So that's how you know you've completed your BCD addition correctly. Questions? Okay, fabulous. Okay, our last topic, I believe, is binary arithmetic. Let me check real quick. Yes, it is. We have a couple of examples, but in the interest of time, I'm going to explain the first one like in detail and then just give you steps on how to do the last one. Some important things to remember with binary arithmetic is that your product is always going to be m plus n bits in size. So if you're multiplying a number that's 4 bits and then with a number that's 9 bits, your resulting product will be 14 bits long. It's always important to make sure your numbers are of the same length. If one is shorter than the other, apply sign extension so that they're both going to be the same bits. This looks like adding more zeros to the front for a positive number and adding more ones if it's a negative number. And you're always going to list the first n plus n non-zero partial products. Usually when you're multiplying these two numbers, you'll just get like a giant string of bits, and it's important to just pick the first n plus n products, partial products. And then when in doubt, check your answer with multiplication. Convert it really quickly if you have some time, and then multiply those together. Okay, so for this example, it's given you two binary numbers, and it also tells you that these are represented in fixed point notation, Q 8.5. So the first thing we're going to do is actually can write this down, 1101, 0111. So Q 8.5 means I have 5 decimal places. So that's 1, 2, 3, 4, 5. I'm going to put my decimal over here. Times our next number is 0, 1, 0, 0, 0. Wait. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 0, 1, 0, 0, 0, 1, 0, 0. I'm gonna write this a little neater so that the numbers are a little aligned, but same situation. So you've got 5 decimals. You're gonna put the decimal point over here. So this is what you're actually multiplying together, not whatever this is without any of the decimal numbers. So I'm gonna write this a little bit clearer. 110 decimal. Nope, that's a 1. Times 010.00100. Okay, and then we're just gonna do bitwise multiplication like we do for regular decimal numbers. So this is going to be all zeros. 2, 3, 4, 5, 6, 7, 8. If you have grid paper, it would be ideal. It's hard to keep track of it once the numbers start getting really long. So 1, 1, 1, 0, 1, 0, 1, 1. Oh, it's important to note that in this example, we were given the exact number of bits that we needed. But if this had fewer bits than the number on the top, you would be adding zeros until you got to the right number of bits that you wanted. Okay, I'm gonna keep going. 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. Okay, those 3 zeros, and then a row of 1s. 3, 4, 5, oops. 2, 3, 4, 5, 6, 7, 8, and our last row of zeros. Okay, now I want to sum these all up. I'm actually going to draw the lines down because it makes me dizzy to have to try to figure out which column is which. Okay, so I'm going to sum all of these up. 0 plus 0, here's a 1, here's a 1, here's a 1 in this column, a 0. A 1 plus a 1 is 2, so one has have 0, carry the 1, and then same thing, 1 plus 1 is 2, oops. So we have 0, carry the 1. We actually have now 1 plus 1 plus 1, so that means we have 1, carry 1. 1 plus 1 is 2, so that's 0, carry 1, 0, carry 1, 1, keep going, 1, 1, and then 0. So this is our answer. So before we put it into the final notation, because we have decimal portions here, we have 5 fractional bits in each of these. So we're gonna put our decimal in 5 plus 5 after 10 for the fraction bit. So from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's where my decimal is gonna go. Oops. So my final answer is 1110, 01, 3 zeros, 11100. Okay, base 2. And then just double check that this is the first, because I have 8 numbers, this is the first 16 non-zero partial products. If there were like leading zeros in front of this, they wouldn't make it to the final answer, mostly because leading zeros are not required. They don't change your answer in any significant way. Okay, so our last slide, I will explain how to do the floating point unsigned addition. I'm going to show you how to do it, and then I'll explain how to do the unsigned multiplication. And then as always, check your answers by converting to decimal. It's the only way that you can be sure that you've done it correctly. So if I have two numbers here that have mismatched exponents, 0, 1, 0, 1 times 2 to the 4, I'm just going to move the decimal place so I can get it to a format that I can add them together. Both of these exponents have to be equal. So let's tackle this one. I'm going to move the decimal point over by 2 here, which makes this 101.01 times 10 times 2 to the 2. And then I'm going to add it to, I'm going to put it over here, 1.1011 times 2 to the 2. Because the exponents match, I can add these numbers together. I'm going to pad it with zeros. So this is 1111 decimal 0, 1, 1, and 1. And this is 2 to the 2. Once I have my addition, I can normalize it. So we're going to just move our exponent over a little bit again. So we're going to say it's 1.101111 times 2 to the 4. So that's our final answer. I'm going to double check, make sure I got that right. Yes. Okay. So for unsigned multiplication, just as with multiplication with decimal numbers, you don't actually care what the exponents are. So I'm going to say 1101 times 2 to the 2 times 1.1010 times 2 to the 4. You're going to multiply by disregarding the exponents. And then let's say this is the number that we finally get, which is going to be 101110010. What you're going to do is first you're going to figure out how many decimals you need to move it over. So this is 4, so I'm going to move it over by a total of 8. So 1, 2, 3, 5, 6, 7, 8. So I have 1.011010 times 2 to the 6th. Oh, I think I messed up on one of the, oh, sorry, I missed 1 0. Hang on, let me rewrite that part. So if you were to multiply this, the answer would be, or sorry, the product would be 1011110010. So when I move my decimal, this is what my product looks like. Then you're going to add our exponent bits, so you have 2 plus 4. So it's important that you add your exponents up here. So what you're going to get is 100010 times 2 to the 6th. Then we're going to normalize it. By that, I mean just move the decimal point over. And we have 1.011110010 times 2 to the 7th. And that would be your final answer. So you do the multiplication the same way that you do it over here. Like same process. Yeah. So I hope this review was helpful. If you have any more questions, feel free to drop our tutoring hours. The most updated schedule will be posted on our posted on our Discord. And if you need to join the Discord, here's a link. No, I think we are okay. Let's see. We were recording audio this whole time. Perfect. How does one get back to